Hello everyone. So in this session we want to investigate some further aspects of shallow water equations. So in the first session I'm going to rescale these equations and make a simpler form of them. And then in the second, and also talk about characteristic curves and characteristic directions in these equations and what do they mean. And then in the next session, I'm going to provide a more general form of shallow water equations in real world cases when we want to do, for example, channel routing or the equations for rivers or channels. Okay. So let's get started. First, I want to rescale and non-dimensionalize these equations that we kind of introduce using some new scales. So for a dam break flow, where we have a dam and then it suddenly breaks, or a lock or gate release, when we release kind of a lock or a gate, we define the following non-dimensional variables. Okay. So say we have a kind of a dam break problem, or again like or a lock or a gate release. So we have something like this. So this is the x direction. And like the water is initially something like this. We have water up to here, say. And then we can have a dam or a lock or anything like this. And then we just release this. We can release it partially or completely. Let's say we completely release this. And then the water starts flowing. And so I'm going to write the shallow water equations and non-dimensionalize them for this flow based on these variables. So the first variable is the initial depths of the flow, which I show it as h naught or h0. Also the initial length of the flow. So these are initial values, initial. And then based on these, I'm going to, I define these non-dimensional variables. So I define capital X as x over x naught. So I non-dimensionalize the length by the initial length. Then I define the non-dimensional u velocity. So this is definition by as u bar, the average depth average velocity which we have. I want to non-dimensionalize it by what? I non-dimensionalize it by the speed of the gravity wave, and I non-dimensionalize it by the initial speed of the gravity wave, which is square root of gh naught. Okay. Then we define the non-dimensional height, or by rescaling h with the initial h naught. So these are all, the capitals are all non-dimensional. And similarly, we define the non-dimensional time by non-dimensionalizing time with speed of the wave, gravity wave, which is c. This is going to give me meter per second, and then over x naught, which is going to give me m, a meter. So this c over x naught is just 1 over time. So instead of c, I'm going to write square root of gh naught over x naught. Okay. So this is just the whole thing is 1 over t naught. You can define it, or it's kind of a time scale. Okay. So we non-dimensionalize these variables, time, with these based on these parameters that I indicated here. So this is a very powerful technique. In general, it's better for any problem, any equation that you have, to write it in non-dimensional form, because then you can get rid of all the units, and it doesn't matter if you write it in a like English unit or British unit or SI. It doesn't matter, and the equations will be the same, the coefficients will be the same and universal. Okay, because we don't have any dimensions and everything is non-dimensional. It doesn't have any dimension. Okay, like here, for example, x over x naught doesn't have any dimension. It's meter over meter. H over h naught is meter over meter. U bar over square root of gh naught is meter over second over meter over second. So everything will be unitless, any dimensionless. Okay, so now I want to just replace this into my continuity and momentum equation, and then get the non-dimensional forms of these equations. So this is my continuity equation. So let's replace these. So instead of h, I am going to write h, capital H times h naught. So partial capital H times h naught over partial t. Instead of t, I'm going to write capital T times x naught over square root of gh naught. This is from here. Plus, again, partial h naught. And then for instead of u bar, I'm going to write capital U times square root of gh naught over partial, instead of x, I'm going to write this x. I'm going to write x, capital X times x0. This equals to 0. Okay. Okay. So some of the terms here are constant, so I can just cancel, they cancel out. So for example, this x naught and x naught here is going to cancel out. The other term that is also going to cancel out is this h naught here, from here and here. It's going to cancel out. So I am only left with this equation, and also a square root of g. This is also a constant, so I can take it out of the differentiation, out of the derivative. So I'm going to get square root of gh naught times partial h over partial t plus partial h u over partial x, and then I can take out square root of gh naught from here, because again this is constant, equals to 0. And so these terms are also going to cancel out. And finally, I will get this equation, partial h over partial t plus partial hu over partial x equals to 0. And this is non-dimensional form of continuity. Continuity equation. Okay. So it's not that much different with the original form, but now everything is non-dimensional in this equation. And based on these definitions that we had, all these terms have no dimensions. Okay. But now if we do this for, let's do this for momentum equation, then we are going to get a interesting formula. So for the momentum equation, we have this. So I'm just going to replace everything. So instead of u bar, I just write from here u times square root of gh naught over, instead of t, partial capital T x naught over square root of gh naught plus u square root of gh naught partial u is square root of gh naught over partial x0 equals to minus g square root of, partial h naught over partial x naught. Okay. So some terms cancel out here. The first one is square root of gh naught is just let me write it down, it's easier. First of all, let me just cancel x naught here because it's easy, so you can clearly see that. And then this term, I can bring this to up here and then also bring this one. And so if you multiply these two together, you're going to get gh naught partial u over partial t plus, and then bring this out of the derivation because this is a constant, so it's going to be u gh naught partial u over partial x equals to, again, bring this out because this is constant, minus gh naught partial h over partial x. And so this term, gh naught, is going to also cancel from both sides. So what I'm going to get is this is partial u over partial t plus u partial u over partial x. And then I will bring this to the left-hand side, plus partial h over partial x equals to 0. And this is non-dimensional form of momentum equation. Okay. So the difference you see here, the main difference is this G is now gone because we have non-dimensionalized it, and everything here is non-dimensional now. It doesn't really depend on the units, okay? And that's the beauty of it. So now we have these two equations. These are now rescaled and non-dimensional. Now I want to write this in characteristic form. So let's write this in characteristic form. So in order to write that, I am going to combine these two equations and write this in matrix form. So the first one is partial over partial t. And then the first term here is what? It is partial h over partial t. So I'm going to write h here for the first equation. And then we have the other term plus. So I'm going to make a matrix here. And here we have hx. Then here we have ux, or partial over partial x, equals to 0. And let me here, instead of this, I'm just gonna write it as this. ht means, ht just means partial h over partial t, okay? And similarly, hx means partial h over partial x. It's another way of writing derivatives. This just makes it easier. So ht, and then the second equation is u times partial h over partial x plus, so this is u times partial h over partial x, so uhx plus hux, right? This is what we have. So if I wanna put it down here, so the first term here is gonna be u hx, and then the second term is gonna be h ux, okay? This is for the first equation, for the continuity. This equals to 0. The second equation is momentum equation. So we have partial u over partial t. I gonna write ut plus, the first one is partial h over partial x. So we have just 1 here. And the second term is partial u over partial x. We have multiplied by u, right? So we have to multiply it by u. We have to write it down here, equals to 0, which we have it here. Okay. So now what I have done is I have now written this in terms of a matrix form, right? Now we have a 2 by 2 matrix that we can solve together in order to solve this equation, this system of nonlinear partial differential equation. So I can define this matrix as A, and in order to find the characteristics of this this equation, what we need to do is we have to find the eigenvalues of this matrix A. So to find the eigenvalues of A, I'm going to calculate determinant of A equals to 0. Okay, so we have to solve this equation. The determinant of A should be 0, so we have u minus lambda h 1 and u minus lambda. This determinant has to be 0. So this gives me this equation, u minus lambda squared minus h times 1 equals to 0. Okay? So u minus lambda squared equals to h, and therefore this has the following characteristics. So lambda is gonna be, or dx over dt, which are these two positive and negative characteristics, which is gonna be from this equation, u plus minus square root of h. So these are the two characteristics for this equation. One is u plus square root of h, and one is u minus square root of h. Okay. So this is important. And let's see, what does this mean? Okay, what do these characteristics mean? So let's say we have this system again, we have this water again. So I'm going to show it in two times. One is the initial time, and then one is later times. So initially, we have a lock or a dam, right? Something like this. So this has a length, can say x naught or L. So let's say x naught. And here it has a depth of h naught. So this is at time t equals to 0, or we can just say capital T equals to 0. And at time t equals to 0, capital U is equals to 0. There is no motion here, right? And then we release this gate. And let's see what happens. Very short time after that, once you take this and release this, what's gonna happen is as follows. So we will have some water that is going to move right, and say this is the initial initial position of that, okay? So now, let's say when t is now larger than 0, but it is smaller than 1. So what does this mean? I'm going to talk about it. So let's say t here is greater than 0, but smaller, let's say much smaller than 1. Okay. So at this point, I can still assume that because it's only a little bit of time, u is small. So u is about 0. So it's not much yet because it's just right after we release this gate, okay? And this again is still h. So what's gonna happen when you release this gate? We are gonna have a wave here, a gravity wave. And this wave is gonna move to the left to inform the left boundary here at the wall that, look, we have released this gate. There is no gate here, and so you have to decrease your height. So the height has to decrease after a while. So once we remove this gate, this wave goes back, something like this. It can be like this. It will go toward the wall, and then inform the wall that this gate has been released. Okay. So we call this like early left traveling wave. And what is the speed of this wave? This moves with speed of the left characteristic, which is c minus, because it's going there. So it's the left traveling wave. So the speed of that is going to be c minus, which is going to be u minus square root of, from this equation, h, right? So this is the speed of this traveling wave, or this characteristic of the flow that moves to the left. And remember, because this is just right very short moment after the release, so again we assume that u is kind of 0. So this is going to be about 0. So the speed of this left traveling wave initially is going to be minus square root of h, capital H. Okay, and it takes about x naught over square root of gh naught. Instead of h, capital H, I'm going to write the dimensional form of that. So square root of h is just, it takes about x naught, or the speed of the gravity wave, initial gravity wave, which is going to be square root of gh naught, for the wave, for the gravity wave to travel to the end wall. So what it means that the initial wave, when you release this gate is gonna take about x naught over square root of h naught to arrive to the wall, to the end wall. Okay, because this was the speed that we got. So it's just square root of gh naught, the initial speed of this gravity wave. And then once this wave hits the end wall, it reflects back, and then it brings the information from the end wall to the nose, which is to the nose of this gravity wave. Okay, so this is what these characteristics mean. These are actually these waves that take information from one side of the flow to the other side of the flow. Okay, and depending on the type of the flow that we have, we can have different regions and different type of information that are kind of transferred between the different regions of the flow. Okay, so in general, our characteristics for dam break flow, so for any equations you might have different characteristics, and this is actually one way of solving PDEs based on characteristic methods that we have in analytical methods for solving partial differential equations. So the characteristics for these shallow water equations is dx over dt is u bar in terms of the dimensional equation, if I want to write it, plus minus square root of gh. Okay, so this is the general characteristics of these equations. So meaning that this is the speed of the wave at any location that is gonna either move forward or backward depending on the velocity of the fluid. Okay, so let's investigate different situations that we might have. First, the simplest case is when we have a subcritical flow. So when we have a subcritical flow, that is when Froude number is smaller than 1. What does this mean? This means that u should be smaller than square root of gh, and so the characteristics for this is going to be the C plus. The C plus characteristics is u plus square root of gh, which is going to be greater than 0, and C minus, the minus characteristics, the negative characteristics, is going to be u bar minus square root of gh. But because u bar is smaller than square root of gh in a subcritical flow, this is going to be negative. C minus is going to be negative value. So in a sense, what we are going to have is as this. So let me show this. So now I am in I want to show x time. So here we have x, but now here we have time. So imagine we are going in time, initial time, and then later times. Okay. So say we have a point at, say, x, like here, a point here in this flow, which is like somewhere like, say, xp inside the flow or inside our problem. It could be, for example, somewhere here, or even it could be here out of the flow. okay? But imagine is inside the flow, somewhere here, for example, or any arbitrary place, okay? So I want to know if I am standing here at, let's say, x equals to p, and then at any time, let's say at a particular time, let's say t equals to, let's say, I don't know, like 10 seconds after this release, I want to see from where I get this information, which regions I am influenced by. Based on these characteristics, you can say that first, I'm gonna have my first characteristic. So first, the most case is C minus curve. So C minus, starting from the initial time, is gonna go somewhere like this. So dx over dt, which is going to be the slope of this, is a negative number, right? So this is the slope of this. So it's a negative number, c u bar minus g square root of gh. This is going to be the slope of dx over dt. So this is a negative number. And so this is my c minus characteristic. So I can get information at time 0 from here. Okay. And then from the positive characteristic, I also can get some information. So I can get the information from upstream, from downstream, using these negative characteristics. And also I can get the information, any information from flow, if I am here. If there is any disturbances here, say, I can get this information from the positive characteristic, right? From this one. So from the upstream, I can get more information. So this is the C plus line. And again, because dx over dt is positive, this is going to be also positive. Okay. And then we have another we can have another regime, and that is if we have a critical flow. So in a critical flow, Freud number is 1. So u bar is equal to square root of gh. So my characteristics are gonna be u bar plus square root of gh, which is gonna be positive, and c minus is gonna be u bar minus square root of gh, which equals to that, so it's gonna be just 0. So let's see what are the characteristics for this equation. So now let me copy this and say if we have Say if we have now again point P. Now I want to see where do I get my information from. So now one of the characteristics is negative, is zero, and the other one is positive. So what I'm going to have is this. I'm going to have this positive one, the C plus one, which is what? Which is U bar minus plus square root of GH. And then I'm going to also have this one. But now this one is 0. So the information is going to be just coming from here. It is 0. So now I want to talk about something which is known as here as zone of influence. So this part, I just forgot to mention that this part is called zone of influence. And it is basically the conditions here affect the flow conditions at point B, at point P. What does this mean? This means that whatever happens here at point P, this is influenced by this zone. At any time, you say only, say at time in the initial time, from here, say x downstream and x upstream at time 0. These are the locations that kind of influence that. Then at later times, say at t equals to something, I don't know, t equals to 10 seconds or anything, this is the region that is gonna influence the dynamics of point P. Similar thing here, we have this zone of influence here now. So what does this mean? When you have a critical flow, it means that you are not going to get any information from the downstream of the flow, right? So all the information that comes in a subcritical flow is from upstream, is from here, is from the left of where you stand. And you are not going to get anything at the, whatever happens here, anything, even like if you have, I don't know, any disturbances that you make here, say you stand here, say this is like flow, and then you are here, and you try to make any disturbances, it's not going to affect, it's not going to influence point P here, because our flow is critical. And there is no characteristic to take that information to the left. Okay? So this is what actually this means. And then the last one is the last situation that we can have is supercritical flow. And let's see what is that and how the flow is going to change there, and what is the zone of influence there. So when we have a supercritical flow, what does that mean? That means that Freud number is greater than 1, so U bar is greater than square root of GH, and so my characteristic one is C plus is U bar plus square root of GH, and the other characteristics is U bar minus square root of GH. This one is positive, but the second characteristic is going to be also positive because we are a supercritical flow. So let's see now how things move. So if we have a point here in the flow, where does it get its information from? So first one is C plus. So C plus is again positive, U bar plus square root of GH. And then the next one is C minus, but C minus is also positive. So what's going to happen? It's going to get it something like this. So the zone of influence here would be here. So in a supercritical flow, all the information are coming from the upstream, from the left. Again, there is nothing, even at that location that it was, no information is going to come at time 0, from time 0. And at time 0, which is here, The only places that are going to be important is going to affect and influence point P is going to come from the left part of that point. Okay, so this is the difference between different regimes and how we can actually gain a better insight into the dynamics of the flows based on these characteristic curves. Okay, so what you actually need to do is, this is going to give us some insight and how the flow is actually moving. And what is the influence, the zone of the influence there, meaning from where that point in time and space gets its information from. So these characteristics will help us to understand it in shallow water equations, in the shallow water, with some shallow water assumptions in the flow that we have. Okay, so this is a very powerful tool in order to analyze these flows without really doing any numerical solution. This is just analytics. Using some analytics, you can get very, very insightful information about the behavior of the flow in later times. And you can even solve this, okay, for some simple, these nonlinear equations, you can even solve them with some simple insights for some simple conditions. Okay, so in the next session, I'm going to give a more general form of these shallow water equations for surface over land flows that is actually typically used in numerical models, especially for hydrological applications.